Next up, continuing CS plus data, we have Yisung Yu. Yisung's one of our newest faculty, and he leads, actually, he's been on campus 2 years, and he's already started and formed an exciting new group, Dulcet, Decision Optimization and Learning at California Institute of Technology. And it's really leading the way for a broad view of machine learning, statistics, optimization, and control at Caltech.
All right, thank you for coming. It's a great honor to be here today. A bit early in the morning for me on a normal Saturday, but nonetheless, I'm quite excited to be here. Today, I'll be talking about automatically improving automation using big data. So automation is something that I'm sure we're all well aware of. It's really changing the way we as a society leverage machines and digital systems and increasingly cyber-physical systems to be more efficient and more cost-effective in the world today. Earliest examples of sort of digital automation include spam filtering, which is arguably the first practical instance of artificial intelligence. Self-driving cars, personal robotics, speech recognition, computational advertising, which is arguably the biggest commercial driver of AI these days. Because it basically forms as Adam mentioned, the foundations of revenue for almost every internet tech company. The Mars rover uses a lot of automation, personalized recommender systems, Facebook, Twitter, etc. Other types of robotics. So the thing that's really driving these systems is the observation that increasingly, even the physical systems live partially in the digital world. They're so-called cyber-physical systems. And when things live in the digital world, software becomes king, right? Software gives you the ability to automatically scale up logic and intelligent systems to be able to drive all of these platforms in a very flexible way. And that's where we come to artificial intelligence. So artificial intelligence is fundamentally about flexibility, right? The old forms of automation were fairly inflexible. And as they become more flexible and you can program them in various ways, within their digital component, then you could have these flexibilities. And fundamentally, the part that really drives it today is flexible pattern matching, right? If you talk to your phone, no matter how you speak, within reason, right? No matter what your accent is, whether you're male, female, young, or old, your phone generally does a very good job at recognizing your speech and converting it into text. Same with spam filtering, same with self-driving cars. These are very, very flexible systems that can do complex pattern matching. That's really what's driving a lot of the next wave of automation today, right? And these systems are not handcrafted. That's another thing that's key, right? These days, these systems are trained using data, lots and lots of data, right? And that is where machine learning comes in. Machine learning is really the sort of the foundational pillar that is driving the development of these artificial intelligence systems, which then create more flexible automation. So what is machine learning? I'm sure many of you know about machine learning. Almost everyone probably have heard about machine learning, but what exactly is it? Well, at a high level, machine learning is the process of converting data and experience into knowledge. Now, data is something that we're all pretty intimately familiar with these days. Knowledge is basically some sort of computer model, and the process is a computer algorithm, right? This is something that lives largely purely in the digital world. So I'm just going to give you a very brief sort of high-level overview of the standard task that machine learning is used these days, and it's a prediction task. So suppose we had an input space, I'll denote by X, and an output space, I'll denote by Y. The goal is to find a mapping, also known as a predictor or a model, that maps X to Y such that prediction error is low on the training set that we've pre-collected to use machine learning on. Right, so examples include falsehood detection. Given if X is a body of text, if we've annotated this body of text as one being false and a negative one being not false, then we can learn a predictor that can say, given this body of text, can I predict whether it's false or not? We can, given some genetic sequence, like a DNA sequence, you could predict whether or not it encodes some function if we had a training data set of this form. Or some molecular compound structure, we can predict some real-valued property of it. You know, if we had training data of this form, right? These are all just sort of XY pairs. Given a huge data set of XY pairs, we find a mapping that maps X to Y. This is how machine learning works fundamentally these days. Okay, and so what I just described is called supervised learning. Supervised learning says we have this large data set of inputs, I'll call it X, some annotations or a target signal that we want to be able to predict, I'll call it Y. And here's an example where it's basically ratings from Amazon. Feed both into a computer, run a machine learning algorithm, which there's increasingly many versions today, and we get a predictor that has low prediction error or high accuracy on this training set. And the types of methods that you can use really off the shelf these days because of the rate at which the field is maturing, things like logistic regression, artificial neural nets, also known as deep learning, random forest and decision trees, and the list just goes on and on and on, right? So this is the state of the art in terms of mass commercial adoption of machine learning today. So for the remainder of my presentation, I'll give you a little bit of a detail about one project that I've been working on in data-driven speech animation in collaboration with the Walt Disney Company. Then I'll go through some of the other challenges and barriers to at the frontier of machine learning research and development that I've been thinking about, and then I'll conclude. Okay, speech animation. So if you talk to an animation artist, such as that DreamWorks or Walt Disney Company, they'll tell you that they spend over 50% of their time animating the face, because somehow if you get that wrong, you're stuck in the uncanny valley and things don't look good. And of that time spent on the face, the overwhelming majority of time is spent animating the eyes and the lips, because that's where you really need to do it well. And so this is extremely tedious, very mechanical, and most artists will tell you that they would prefer not to be able to do this, not to have to do this, because it really doesn't offer much room for creativity, right? It's just a very mechanical and tedious process. So let's see if we can animate part of this, or excuse me, automate part of this, right? So that the artists don't have to do this anymore. They can spend their time on more creative and productive endeavors. And we'll focus on the mouth, the lips. So the problem with lip animation or lip sync, automated lip syncing to audio, is the problem of co-articulation. Co-articulation is the challenge where if you have a sequence of phones or syllables, the way the mouth is shaped for any specific syllable is highly dependent on the neighborhood of syllables that surrounds that syllable. That's the co-articulation challenge. And this is just one example for the syllable K. And I'll just, hopefully the audio works here. Okay, so just hopefully you get an idea this is hard, right? If you want to manually create like an animation model to animate automatically and you hand engineer this, you're going to have to basically go through countless numbers of corner cases in order to get something that works well, and people just simply can't afford to do that these days. So, but can we do this, right? Can we actually solve this problem? And so here is an example of our approach that we recently developed in the past couple of years.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
So this is our face model. It took as input an audio from Barack Obama's speech about the British BP oil spill from a few years back, and it automatically lip-synced to some audio. Right. I'll just play it again.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
Okay, so how do we do this? How does this work? So we collected training data, right? That's how machine learning works. We hired this actor in collaboration with the Walt Disney Company. His name is Ken. We asked him to sit in front of a high-def tracking camera, and we captured his lower jaw speaking about 2,500 American English sentences. Recorded at 30 hertz, that's about 10 hours of recorded speech. He was a very tired guy at the end of the day. And then using standard computer graphics technology, we built a digital model of his face, which has about 30 degrees of freedom in our initial approach. Our more advanced models of his face has about 100 degrees of freedom. Right? So it's a very flexible system, right? And so this is just an example of the training that it looks like, right? This is a frame by frame of the word X-ray vision, and then you can see the ground truth of how his lower mouth deforms in response to this sequence of syllables. So the prediction task is as follows. The X is an input sequence of phonetics or syllables, and the Y is an output sequence of parameterizations or configurations of this face. And so each token in the sequence for Y lives in a 30-dimensional space if the face model has 30 degrees of freedom, or a 100-dimensional space if the face model has 100 degrees of freedom. And the goal is to learn a predictor H that maps from X, which are sequences of tokens, to Y, which are sequences of basically high-dimensional trajectories. Right, this is what it looks like. Here I'm visualizing the first dimension of that 30-dimensional parameterization, which basically corresponds to how wide open the mouth is. So as you say the word prediction, first the mouth starts closed, sharply opens, then smoothly tapers off, and then it closes. Right. So this is basically how this training data looks like. So there's a few properties that when we looked at this data set that we sort of observed and then we later exploit it, right? One is that you really, really need to model the local temporal curvature extremely well. This is the co-articulation problem, right? Because the way the mouth animates depends a lot on the neighborhood of syllables that you're speaking, and it can vary in arbitrary ways, seemingly. Right, so we really want machine learning to capture this flexibility really well. On the other hand, there are minimal long-range dependencies. How you say the end of the word prediction is more or less the same as how you say the end of the word construction, election, and so on and so forth. So there are minimal long-range dependencies in this problem. So what that means is we want to build a machine learning approach that really nails the local dependencies and it can largely ignore the global dependencies. And that leads to our approach, which is called an overlapping sliding window approach. We take our sequence, we cut it up into overlapping sliding window sequences of fixed length. In this simple example, it's length 5. We feed each overlapping sliding window sequence into a machine learning algorithm. In this case, it's the decision tree. We've also used deep learning and neural nets. And the decision tree maps the fixed length input to a fixed length output. Here also length 5. So it's basically a 150 variable regression problem. Still highly non-trivial, but something that you can actually solve using off-the-shelf packages such as scikit-learn and TensorFlow and so on and so forth. Finally, we aggregate the predictions into our final output, and this is very fast. So this whole pipeline, after you've trained it, basically runs in real time at test time. Right? And this is the only thing that uses machine learning. What we've done is we decompose or reduce the problem to something that's much simpler than the previous problem. Okay, so here's just another example.
And tonight, I've returned from a trip to the Gulf Coast to speak with you about the battle we're waging against an oil spill that is assaulting our shores and our citizens.
But of course, people at these animation companies do not care about Ken's face, right? They care about other types of faces, right? So can we map the animation of Ken's lips to the animations of arbitrary digital virtual characters, right?
Do I look funny to you? I may be a chimp, but I'm dressed better than you.
I'm a PhD specializing in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organization.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português é ainda melhor, não acha?
So our model maps phonetics to the mechanics of lip syncing, right? It doesn't actually care about the language you're speaking. So our approach, in principle, works for any language. We've done this for Chinese, Korean, German, Spanish, Portuguese, Italian, the list goes on, right? So what this means is that if you want to release your next animated movie simultaneously to 150 countries, we can, instead of having this awkward redubbing where the lips don't match the audio, we can simultaneously animate and synchronize the lips to any language, essentially for free and in real time.
So are you rich?
There's a number of software engineering challenges. And what I've given you is a prototype. Okay, so let me just, okay, so maybe I'll just take 1 second to address the question of sort of the challenges to translate this prototype to a commercial product. And then I'll quickly move on. So the challenges are that in order for this to be truly production quality, we really need to collect training data for every language. What I've done here is I projected Portuguese onto the English phonetic data set, right? Which is okay. It looks great. But when you do it for things like Chinese, I'll show you an example in just a second. Actually, I'll show you right now. When you do it for Chinese, it looks a little bit off. It still looks much better than anything anyone else can do, but it looks a little bit off.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
So that's me speaking Chinese, right? And those of you who understand Chinese will think that's funny. But my point is that in order to do this really well at production quality, you really need to recollect this data in Chinese, in Hindi, Arabic, etc. And there are many different dialects of Arabic, right? If you want to do this for British English, you really want to collect how a British person would enunciate these syllables rather than American English. So in order for production quality systems, you need to really scale this up. And this is really just a prototype that demonstrates a proof of concept. But maybe I'll get back to you in 5 years and let you know. And we could also do things like singing.
Somewhere over the rainbow, way up high, and the dreams that that you've dreamed of once in a lullaby.
All right. So, in my remaining 5 minutes, let me just sort of highlight some of the other challenges and opportunities at the frontier of machine learning and artificial intelligence that I've been thinking about. So, by and large, most people who've used machine learning use it for very simple outputs, right? Here, the y is the single number, right? In the previous example I showed you, the y was a high-dimensional trajectory that spans multiple time sequences, right? So most of machine learning still focuses on very simple outputs. How do we talk about more complex output spaces or structured outputs? Machine learning only learns using input-output examples. This is one of the fundamental limitations and also the fundamental sort of the power of machine learning, which is that it can just learn anything using input-output examples if you give it enough training data, enough input-output examples. But if you don't have enough, then you can't actually use machine learning effectively. When we learn, we don't learn using input-output examples. We learn using lessons and principles and sort of general rules of thumb that we then fine-tune using input-output examples. Machine learning these days don't do that. And finally, how do we get away from this pre-collected training data? And so I'm just going to quickly give an overview of another project. This is actually one that appeared on Sports Illustrated. So the idea here is that we have a human camera operator who's broadcasting a game, in this case a basketball game. We have a real-time player tracking system. And the goal is to train an autonomous robotic camera that can mimic the behavior of the broadcast camera operator so that you can compose production quality footage of a sports game, right? So if you use the standard supervised learning approach that I described in the beginning of this presentation, you get something that looks like this, right? It's very jittery. So the blue line is the ground truth. The red line is the prediction of the system. It's very jittery because the system doesn't know that smoothness is something you care about, right? You could teach it that smoothness is important using input-output examples, but since this is a continuous space, that requires infinite training data in the worst case. Even in the era of big data, no one has infinite training data, right? And so what's the problem? As I just said, it takes infinite training data to train these smooth models using only input-output examples. In practice, people do post-hoc smoothing, like a Kalman filter and so on and so forth. Unfortunately, methods like Kalman filters make very strong modeling assumptions, and like Gaussian this, Gaussian that. And so they cannot actually flexibly condition on context, like where the players are, right? Those are very noisy detections. And so this context-free post-hoc smoothing either over-smooths or under-smooths depending on whether there's a change of possession, fast break, and so on and so forth, right? It's a global model of smoothing, not a context-sensitive model of smoothness. So, I've been studying hybrid model-based, model-free approaches recently. Model-based approaches have strong assumptions, can be fit using very little training data because they have strong modeling assumptions, like Kalman filters, but they lack flexibility. They cannot condition arbitrary context. Model-free approaches, like modern machine learning approaches, deep neural nets, random forests, are assumption-free, can learn anything if you give it enough input-output examples, but it requires a lot of training data, and in general, are underspecified. Can we get the best of both worlds? And so this is our result. We trained it using only 30 minutes of data on the basketball game, where the blue line is the ground truth of the pan angle of the human camera operator for this sequence of basketball plays, and the red line is our robotic camera prediction. And if you're interested in details, this paper was recently published at the International Conference on Machine Learning. So the benefits of hybrid approaches is that we're not throwing away all the models that people in these domains have worked on for the last 30 years, right? Because these models are pretty good, right? It's just that they can't flexibly condition on arbitrary context, right? Because they have very strong modeling assumptions. And so we use a model-free component like deep learning to merely course correct as the model-based part drifts from the correct prediction. And this requires significantly less training data than using deep learning all the way end-to-end from scratch. I'm going to conclude by talking about a project on personalized machine learning for treating lower spine injuries. So this person is a spinal column injury patient. His spine is bruised. He cannot walk or stand on his own. He needs help. And so my colleague Joel Burdick has been working on this medical device that is basically an epidural electrostimulator that's implanted inside the spinal column and basically induces an electric field that amplifies the signal from the brain to the lower limb so that this person can regain some of his lower limb mobility. The problem with this medical device is that, again, we're living in a cyber-physical system where this device is extremely flexible. You can induce so many different kinds of electric potential fields, and every patient is unique. every injury is unique, so we can't use data from one patient for the other patient. We need to collect data on the fly for each individual patient. So this is a personalized recommendation system problem. So we combine forces to treat this type of clinical treatment as personalized recommendations, where we interactively apply stimuli and receive response and hopefully quickly personalize into the specific injuries of the specific patients. And so this device is in clinical trial. And so this is a regime where it's so complicated that human doctors really don't have, their intuition breaks down, right? Because there's so many little knobs to turn. And so this is just one result from a human expert and one result from our algorithm, right? And so it is, these are preliminaries, but they are very promising. And so putting everything together, this is sort of my view of where AI is going in the next 5 to 10 years. We have the initial set of training data, large but incomplete. We have our model-free approaches, the powerful machine learning approaches that have been proven to be very useful in their specific context, such as neural nets. We have these models that people have built over the last 30 years that they're unwilling to give up on because they preserve properties that people care about, like smoothness. We often have a simulation oracle that we can use to collect more data. And then we need to develop interactive learning approaches that figure out how to combine all these together to have both to make the best use of the initial training data, to leverage the properties given to us by the model-based controllers, and to use deep learning and random forests to add a layer of flexibility to these approaches with as little extra training data as possible. So thank you very much.